We are going to discuss today an example on energy method using uh, unit load method, the virtual work method. So, in this example, we'll be talking about simply supported beam, where the beam is not uniform. You can see this uh, up to 5 meters. It's having 2 EI. Uh, and then it's becoming EI. So the material would be the same. So probably the I value, not the area is two times. I value is two times, right? So don't get wrong if I and two I there, right? It doesn't mean that this if this area is A, then this area should be 2A. It is wrong fundamentally, right? So one thing possible is, I value is, if it is a rectangular, let's say it's a rectangular, so it's PD cube over 12. So you can see if the depth become twice, you can see the D cube will be 8D cube. So if others remain same, you can see that I value becomes 8 times I, right? If this is I, this is 8I. So this cannot happen. So this can happen. So how this value should be 2D cube at the end if it need to become 2I. So you need to take the third root of this as the D value. And then when you uh, take the third power, it will become 2D cube. So this is bit complex, right? You don't need nothing much to do because you can simply multiply this by 2. So that means if you uh, take the breadth value twice, right? Because it's breadth b to the power 1, right? So b will become only b, 2b. It's same as earlier. So if this is I, then this is 2I. So you can see, right? For this case, your area will be twice as well, but it does not mean specifically that it should be 2 times area, because if you plot this like a beam, it would look like this. So your B is like this. So your depth is same. What happens is B becomes twice. So you can idealize this beam something like this, right? This is 2B. In this case, this area is 2BD, the cross section area. This is BD. So in this case, it becomes twice the area as well, right? But it's not necessary to be that, right? So first thing we need to do is we should find the reaction. So this is apart from the geometric asymmetry. So the loading is symmetric. So you know that the support reactions are not dependent on the material properties, so that you can find the reactions. If it is 20, this would be 10 and 10, right? So this is easy, just a simply supported beam where the middle is loaded from 20, since the loading is symmetric, right? And the reactions does not depend on the geometric change, right? So it doesn't matter what happened to the beam. If you have something like this beam, right? Let's say this is 3i and ei, 3, let's say this is 3ei and this is ei, doesn't matter, whatever, or else this is a uniform beam, does not matter, your reaction is same as in each case. So that would be 10 kilonewton and 10 kilonewton, because these two, summation of these two reactions should equal to 20. And when you take bending moment about one of the points, so this would become 20 into 5 plus, let's say this is Ra, so 20 into 5 into Ra times 10, right? So you can see Ra becomes 10 and then Rb also will becomes 10, right? So what we do on the unit load method, so I have discussed in previous videos, right? Please check those. I have discussed the theory parts previous videos, right? So that please check these. All the theory parts necessary are there. The unit load method and the Castigliano's theorem to find deflection and the slope. So to find the deflection underneath this point, you can choose, we will use virtual work, the unit load method. So what we know is we disturb the structure. If I tell you concisely, so you have 20, so you need the same deflection underneath 20, so that you disturb the structure, right, at 1 kilonewton, right? So let's say this have a deflection of delta, right? And the work done. So you know the strain energy in a beam is dependent mostly on bending, right? So that you can write an equation. So this is the disturbance force, right, into the actual displacement. So we know the assumption made in this complementary theory is that displacements are fixed, right? So if you apply a virtual force, so very little, so think about a very little force, right? So if it is 1, and then the work done by that virtual force is 1 into delta. So wherever we need to find the deflection, we should add unit load, right? So I have discussed in detail. Please check these videos. The links are given in the description. And then that is equal to the strain energy. So why we need integral is the bending changes from along its length. Unlike in a truss, we use sigma. Why? Because you know within a member the axial force is constant, so that you can sum it up each and every member, because the within a member the axial force is uniform. But here you have, even if you have one member along the length, the bending moment changes, so that you need integration, right? So we have develop an equation. So this delta M is the moment caused by this unit force. And then M over EI means this moment is the moment caused by the actual loading, right? So you need to interpret this. So first we need to derive an expression. So you can see that this point load is separating this beam into two portions. Within this part, you don't have any loading or bending moment, right? So that you can write one expression for the bending moment and as well as for this case. Right here also the same, right? So I'll write this part. So I'll apply a clockwise moment, right? So once you apply a clockwise moment, so you know there's a reaction of 10. So you can write the moment equilibrium of this portion above this point, right? So M plus, let's say this distance is X measured from the left end, and X equals to 0. So M is minus 10X. And you can see this beam is pretty much identical to beam, right? What happens is only the loading becomes 20 to 1. So the ratio is 20 to 1. So that means you should so what happens is actually you should divide this part by 20, or else I will write the equation if you can't do that. Let's say M, because the reaction is 0.5. 0.5 because 1, 0.5 and 0.5, right? Okay, so if you write an equation, so that would give you M, this is X, moment about this point. So M plus 0.5 into X is equal to 0, and M is X, right? So you can see this is divided by 10, right? Each equation, because M, you can't divide M by 20 because that's an unknown, right? So that's why I didn't divide. If I divide it, I'll write that as M dash. So then you will be confused what is M and M dash. So that's why I didn't divide if I want, because that's my simplification. So so for the second half, you can write an equation same as this, and you have a bending moment of M. For this part, you have bending moment of M, and then you don't need to cut it from these places. And the X is measured from here to here. You can write an expression using that M plus 10 times X, and then this point load is also coming 20, that is anti-clockwise, 20 times X minus, this is 5. X minus 5 is equal to 0. So your M should be M is going to be, when you simplify it, 10x minus 100. Similarly, you will get an expression m 0.5 into x minus 1 into x minus 5. So you will get an expression like 0.5 x minus 5. Right? So these are your expressions. This is so these parts is from 5 to 10, both these, right? This is from 0 to 5. Now you can go ahead and define your equation. So 1 into delta is the when the moment occurred by the virtual loading, right? So we need to separate these two equations because it's different from 0 to 5 and 5 to 10. You have two equations, two separate solves, right? So you can write 0 to 5, 0 to 5, this is going to and the moment is by virtual loading, it's minus 0.5x into m over ei. So m is the real bending moment, right? Minus 10x. Over this is 2ei. This is where you take that into account, right? This is where you take into account 2ei. So you have then 5 to 10. The bending moment is, let's say you had, this is the virtual moment, right? 0.5x minus 5. And then m over ei. This is the bending moment of real system. That is going to be ei. So now it's just a matter of simplifying everything, and that should give you the bending moment. So this is, so the deflection 1 into delta. So this is delta. So you can take minus 10 and 0.5 multiply and out. So 0.5 into 10 means 5. So you can take 2ei also out. And then your integral remains x squared from 0 to 5. And then you can take a second integral, and you can take 0.5 out from this part and 10 out from this part. 0.5 into 10 means again 5. This is 5. And take EI out. Okay. So your integral remains like this, 5 into 10. This is, if you take 0.5 out, this is going to be x minus 10. This is, if you take 10 out, this is going to be x minus 10. So whole thing is going to be x minus 10 squared. So you take EI out. Take EI out, and now you can integrate this. So this is going to be x squared or x cubed over 3, and the limits 0 to 5. This is going to be x minus 10 3 5 to 10, right? So if you apply 0 limit, you know that it's going to be 0. Doesn't matter, I write that. So this is going to be 125 minus 0. So this is going to be 5 over EI. 5 over EI, and then if you apply 10, everything is going to be 0. If you apply 5, so that's going to be minus 5 to the power 3 over 3. So that's minus power, brings you minus 125 over 3. Right? So that will give you, so you can take 125, 5, that means 625 over 3, 6 EI out. Right? So that's going to be you can take 5. So 6 in 5 into 125 means 625 over 3 EI. You take it out. Okay. So your remaining half. Okay. Plus 1. And that should give you 625 over 3 EI over 3 over 2. Right? So 3 cancelled. So your deflection is positive. So that means the direction where you applied the virtual force is downward direction. Right. So this is your deflection. And you can, in the same way, you need check for the end slopes. So I will check one of the end slopes, right? Let's say I need this theta. So that also you can, it's possible to obtain it from the energy method. So what you need to do is, so your linear displacements are correlated with linear force. So your rotational displacements are corresponding to a bending moment, so that you need to apply a bending moment, a unit moment at the place where you need to find the rotation. So I'll apply a unit moment here and I'll do that. So I need to find the rotation at here, so I'll apply a unit moment. Okay, so if you apply a unit moment, there will be two reactions, and there's no other linear force, right? So that these two reactions should be, so let's say this is RA and RB. So taking the vertical reaction, so RA vertical equilibrium, RA plus RB is equal to 0, no other force or loading, because this is a bending moment. So you can take bending moment about this point. So that's going to give you RB into 10 is 10, that's anti-clockwise, plus this is a clockwise moment, 1 is equal to 0. So RB is 1 over 10. So RA is negative 1 over 10. So that means it's in downward direction, right? It's like this. 1 over 10 is, now I have drawn it in the downward direction, so that I don't need the sign, minus sign, because earlier I draw it in the upward direction. So now you know, now you don't need this because you have found the, so you can see within these portions you don't have any moment, or because this is added at one end, so that you can write one expression for the entire bending moment, because this is added at this point, right? So you can write one expression for the entire bending moment along beam. So in that case, you will obtain m plus, this is 1 minus, this is anti-clockwise, let's say the distance is x. So m is so if you bit simplify, this will be x minus 10 over 10, right? So this is valid from 0 to 5 as well as 5 to 10, because this is the expression derived for 0 to 10. So it doesn't matter if you divide this to two limits, because we need that, because the actual loading have two limits, right? So this will be the bending moment, so that you can write the same expression, virtual work method. So now the virtual moment into the original displacement in the actual system is equal to, so this will be the 0 to 5 So, virtual moment, it's not going to change. So that's x minus 10 over 10, right? So the actual bending moment does not change. We took it in the previous example, 10 times x over 2ei. So whatever is there, right, either deflection or rotation. So this is strain energy. Strain energy is corresponding to the bending moment, so that you don't need additional part, right? So this is not going to change. What happens is here always the bending moments will be there in this side because of this strain energy, right? So here the change happens virtual moment into the actual rotation, right? Plus, so I have explained. If you don't understand this equation, please check the previous video. I have provided the links that you can understand each and everything, how to derive that equation, right, using Castigliano and virtual work. So the bending moments from virtual, it's not going to change. X minus 10 over 10. And this is going to be 10 x minus 100 over ei. So you can take, now this 10 is cancelling. You can take minus 2ei out. And your integral remains like 0 to 5 x squared minus 10x squared minus 10x, because you take this minus into outside, right, and 2ei. So here also you can cancel this 10, and this will also be 10. So x, so you can take 1 over ei out, and it's going to be x minus 10 to the power 2, the same integral that we obtained before as well, 5 to 10. And this is 2ei cube over 3 minus 5x squared. So x squared over 2, that's going to be 5x squared. This is going to be the same integral as it is. To 10, right? So this 2ei, if you apply 5, so that's going to be 125 over 3 minus 125. And if you apply 0, it's going to be 0, right? Is the whole limit, and then if you apply ei, so if you apply 10 here, so everything is going to be 0, and minus, then it's 5, so that is going to be minus 125 over 3. So this is going to be 3 times, so you can take out. So this is 1. So 1 means 3 over 3. It's going to be 125 over 3. So minus 2 into 3. So minus 2 getting cancelled. So minus into minus plus. The same thing occurs again. EI. So your answer is 250 over 3EI. So if you know E and I, so that's positive. So that means it's along the direction you apply the virtual moment. So that means it's like this, right? So it originally have the displacement in clockwise direction. Okay. And this is your rotation. You can do the same thing to here as well. Okay. So what you need to do is repeat the same thing. Instead of apply moment at here, apply a clockwise moment at here. Okay. So clockwise, take clockwise positive. Okay. And do the same thing. Sometimes you will obtain this theta as negative because you can see the beam is bending in this fashion. So your theta should be negative actually. But if you apply clockwise unit moment, the theta should look like this. And this is positive, and your final theta value will be negative, giving you the answer should be in anti-clockwise direction. Thank you.